Same.
Yeah.
Okay, so to wrap up the day and kind of our introductory concept talk is about really kind of RF and analog computing. So I invited Bob McGwier here to talk about that. For those of you who don't know Bob McGwier, you will.
Okay, so I'm going to talk to you about, well, so RF and radio started slowly. So I'm going to give you some history. And like all the pieces that are happening now, everything's happening at light speed, so the end of the talk goes at light speed. So anyway, I'm the Director of Research at the Hume Center from Virginia Tech. We're one of the sponsors, and as Tim did his plug earlier, I'll do it again. I'm hiring. Typically you need to be a United States citizen or a green card holder to work for me, but it's fun to work for me. Okay, all right. So I'm going to have to read my own slides, so I'll do it like this. Okay. These are Maxwell's equations. They tell you things about changing electrical fields, changing magnetic fields, static magnetic fields, and static electric fields, and how they relate to each other. And I know you came here for me to tell you all that, but I'm not going to. So you didn't come for a lesson in physics from Einstein, which I've never been accused of being, but you did come to learn something, so I'm going to try to teach you something. Okay, so what's a radio? You are doing software-defined radio. You might as well figure out what a radio is and where they came from and how they got to be and how we got to be here before we move into what's going on right now. So a radio is a system where we have a source and a sink, a source and a destination for electromagnetic emanation. If it's a wire, it's not an emanation, you don't have an antenna. Okay? But if you have a wire, you can still put EM down, it's just not what I call a radio. As an intended destination, usually. The source is a transmitter, usually. So you can have a source that's not a transmitter because it wasn't meant to be an emitter because it's interfering with your receive system badly. So you can have unintended and intended. But never mind, if it's emanating, it's a transmitter. And the destination is a receiver mostly. Sometimes signals go into poorly welded joints in the building and they're rectified and clobber equipment all over the building. So that's an unintended receiver that is demodulating the data. Okay, so a light bulb is an optical transmitter. And remember the blinking lights on ships from in the Navy where they were blinking out Morse code as they plowed through the German and Japanese subs and others? Okay, glad those days are over. You could have light amplification, like stimulated emission radiation, or a laser feeding fiber optics. So with most things in the radio, we consider RF, or radio frequency systems. This is the patent on the spark gap transmitter. That is a picture from the spark gap. Basically, you had a thing that generated a whole lot of ugly sounding noise. It was just horrendous. And it's actually, you could see the sparks as the wheel would go by and generate these massive sparks. And they didn't want to transmit over every single band there was with this system, so they would put a tuned circuit after the spark generator. And the tuned circuit would focus the RF coming out of it a little bit. A little bit. And well, now that they figured out that they could take this energy from this massive spark plug and focus it a little bit, we can use this to send messages. So they even had binary systems back in the ancient days. If the key was down, it was on. If the key was up, it was off. So they would sit there and risk killing themselves with kilovolts across these contacts as they would go dot, get, dot, get, dot, get, dot, and send Morse code from ship to shore, shore to ships, etc. They didn't put many spark gap transmitters in the early airplanes. They were too heavy. They would catch things on fire, arc, burn the plane, so we didn't do that. We put them on ships where they only killed sailors who were trying to send Morse code with 5 kilovolts across the contacts. Okay, so this is the first transmitter, patented way long ago by Shoemaker. All right, so transmitter for wireless electromagnetic emission. First one was spark gap doing Morse. Had an oscillator to generate some frequency, and it had a filter to keep it kind of focused. It has a method to modify the RF oscillator to convey a message. As I said, it turned it on and off. So that would be the way the thing worked. And it had an antenna. An antenna. So what does an antenna do? Well, if I run an alternating current into a piece of wire and have a closed circuit with a little feedback from my ground system, and the current flows through the antenna, I know you paid attention to that first slide where we had Maxwell's equations up. What happens if I change a current in a wire? I change the magnetic field around it and it emanates. Okay, so I'm taking current, running it through this wire. A Maxwell equation says when I run current through a wire, especially if I change it, I change the magnetic field and the magnetic field takes off. That's how an antenna works, okay? But you want power to go out because I want you to be able to hear me when I get on the other side. So I need to design my antenna in such a way that it is apparently sinking a lot of power. So how do I measure power in a circuit? Give me a good equation for power. I squared R. So if I am radiating, it's an effective resistance. Because some of the power leaves the antenna and goes off into the ether. That's called the radiation resistance of an antenna. I have current going through the wire or the pipe or whatever's in the antenna, and however much it emanates is like a resistor, because it's dissipating power to the ether and beyond, and that resistance is called radiation resistance. So your measure of how good an antenna is doing is if you maximize the power transfer to, if I have a sink and I have a source, how do I maximize the power transfer? Match the impedance. That's exactly right. I maximize power transfer when the source and the sink have the same impedance. So you want as much of the sink to be radiation resistance as possible. Now, I don't want it to be a 50 ohm resistor. I want it to actually be radiating. Okay, so I don't want to be turning it into heat. I want to be turning it into electromagnetic waves. So all that stuff goes into the design of an antenna. And you have to remember, people will they had Maxwell equations and a few experiments and spark gap transmitters, and they were trying to figure this stuff out. And they did it pretty much by the seat of their pants, just playing around. So not much has changed, believe it or not. With the exception that much of the preparation of the message nowadays, including the waveform, is done in a computer. Let's go over some of this. Well, look, this is the receiver, which is the hard part. This is the King Cross super heterodyne receiver. And why do I have the King Cross super heterodyne receiver up here than the Howard Armstrong super heterodyne receiver? Why? He was like a ham. Armstrong was as dumb as a ham. So back in the 1980s, when, who knows Phil Karn? Okay, when Phil Karn and Tom Clark and me and a bunch of other people, we were doing packet radio. And we started the Tucson Amateur Packet Radio Group. And we did AX25 link layer and then AX25 network extensions and all that stuff in the 1980s. And then turned it on to Bell 202 and Bell 103. Horrible crap. Oh my God, it was horrible. Except for the work we did of transferring data from one computer to the other. GPRS Edge is a 100% verbatim lift of what we did. verbatim. We didn't copyright, we didn't patent, we didn't do anything. Howard Armstrong in 1918 invented the super heterodyne receiver, but did not patent it. Okay, so he made a mistake, King Cross patented it, and there you go. And he did this at King Cross did it at the demand of General Sarnoff of RCA. And what happened eventually was Armstrong basically couldn't take it anymore, and he decided he would do a high dive from the 50th floor. Okay. All right, so a receiver, super heterodyne receiver, I said patent, I should say without a patent. That's what happens when you type a slide at 3 o'clock in the morning. So he perfected the basic circuit, and this job is much harder than a transmitter. Really a whole lot harder. A transmitter has, with your arm connected to it or your computer or whatever, it has knowledge of what it is about to do. The receiver's job is to take some partial set of information and guess what you did. That's the you're guessing what you did, and the transmitter is the conveyance of the message. Okay. So, and typically, I have to receive this message after it's traversed a long distance. So it's weak. 1 over r squared is not your friend, and typically it's worse than 1 over r squared in the real world. So not much is actually free space. It's usually r to the 2 plus something or other, especially on microwave bands or high UHF bands where we have cell phones. It's not really 1 over r squared. Free space just doesn't exist where our toys are. Okay. All right. So, and furthermore, I have to know something about where you're transmitting, or what frequency you're transmitting on, because do you think I want FM radio and every television station and every police and fire truck, etc., coming in my receiver or with your message? No. So the filtering out of all those other signals is the selectivity that is provided in a receiver. So your job is encode some message, receive some message by selecting out the frequency of interest, and then I might move it with a mixer to a frequency where it's more easily processed. So if I transmit a signal, an audio signal at 1 gigahertz frequency, center frequency, it's really hard to hear the audio when my sinusoid carrying it is a gigahertz. So I have to mix it down to close to 0, and then I can do some easy stuff. What is that easy stuff called? Absolute value. So if I take the absolute value of an amplitude modulated signal, especially one that's modulated or brought down to near 0, I get AM out of it. Okay, so that's how an AM transmitter works, or an AM receiver works, is I move it to some place where I have easy circuits, and then I just take the absolute value of the signal and have an AM demodulated signal. That's the crummy way of doing AM demodulation. There's a better way, we won't go over. Okay, so look, many are still super heterodyne these days, these receivers, but we've had a revolution take place. The revolution is that parts have gotten smaller, the computers that are behind them have gotten faster, the analog to digital converters have gotten where they can do a much, much better job of converting everything from strong signals to weak signals into digital numbers. And I can easily put something in front of these ADD converters that makes them sensitive enough to hear weak signals and linear and resistant enough to take strong signals at the same time, and allow me to do the selectivity, the decoding, detection, etc., all in software. So nothing's changed except everything's gotten smaller and the ability to do things has gotten faster. And the other thing that's happened is a super heterodyne receiver system had to have cascaded stages. It had to have a couple of mixers, and things move up and down, and filters and all sorts of stuff. And every one of these stages in a super heterodyne receiver, there's no such thing as a linear analog circuit. It doesn't exist. Every one of them has nonlinearities. Every single real analog circuit has nonlinearities in it. And much of what we do when we characterize the receiver's performance is measure how linear they are by measuring things like IP3 and IP2 and The other thing they have is that they have a bunch of oscillators in them, especially if you want, because you remember you're going to mix things up and down. The oscillators introduce noise. That's phase noise if it's synthesized. So all of these things are really, really, really bad. They multiply, they mix, they add nonlinearities, noise, and distortion to the incoming signals in these super heterodyne receivers. So one of the best things that happened as our A to Ds got really, really fast and really, really good, very deep, high dynamic range, is the linearity happened, and we weren't mixing these weird signals all over the place. So that has made having good receivers really, really neat. So when we're mixing the baseband, we can eliminate some ugly problems with images nowadays. That's Fred Harris and I and many others have come up with algorithms that run inside these parts, these RFIC you buy for analog devices. Several of us have a lot to do with that. Okay, so we no longer have a huge dynamic range issue because these ADCs, they have lots of bits in them. And I'll take these lots of bits and I can run them into a very low power computer of some type, like an FPGA or GPU or even a general purpose processor. And I take these big, huge signals, big, fast signals, and I run them into this computer, and the computer does channelization. And the channelization it does is, you have this much signal territory, and you want to only look at a little piece of it. You can focus what's going on around this little piece, and you get a win. You get a huge win. By taking and averaging things out, the noise power drops away, you've filtered out noise power, you've done all sorts of things, and you increase the dynamic range just by letting your computer look at that piece. So they get very high dynamic range. All of this is very good stuff. So RFICs are a revolution, and so are these high-speed ADCs, and the FPGAs and the ASICs and other things that are around the processor. You are benefiting from all of this happening. Charles Clancy and I, before we were working with Tom, and then brought him into the Good Radio family as a director. First he worked with us at the Institute for Defense Analysis, and then decided to become the director of Good Radio. Right about the same time we were starting ACFest. We were looking at this stuff, and we had an important person in the government ask us, can we do a problem? And we told the partial truth. The partial truth was, yes, we can do this problem, and we will take this much time to give you the solution. And the reason it was going to take that much time to get to the solution is we were looking at Moore's Law and saying, at the end of this period of time, Moore's Law would give us a processor that was fast enough to do this. That was right about the time Tom left IDA, became the director of Good Radio. We delivered what we were supposed to deliver and made everybody happy, but we had to wait 3 years for Moore's Law to catch up. Okay. All right, so you can finally have high-performance transmitters, receivers, in a really, really small package, which is these RFICs. And you can, and as Matt shows you, when it has this UBX or his RFICs in them, you can shield the receiver, which is to work on really, really weak signals, from the transmitter, which is not much 1/r² loss between the transmitter right next to the receiver, but you can shield them well. You can isolate them. So the transmitter that's sitting right there on this little die that's about yay big doesn't overload and clobber the performance of the receiver. I don't think you understand how hard that is. It's hugely hard. They have to have nearly 100 dB of isolation between that transmitter and that receiver sitting on the same part. It was the engineering problem that had to be solved. The problem was getting those things sitting right next to each other, with the transmitter putting out a thing that was tens to 100 dB stronger than the signal of interest it wanted to listen to. And they have both the transmitter and receiver on the same part, and it can transceive. The phase noise from the transmitter does not kill the receiver. The overload does not happen. It was a massive, fantastic piece of engineering, and most people don't understand how hard it was. But it's that thing that Analog and Maxim and others have done so well for us that has utterly transformed what we have in our hands now. because we can put these general purpose computers behind them, take these massive, awesome transceivers that take, a microwatt to run them, or a milliwatt if you're going to put out a milliwatt of power, and then have all this fantastic stuff. Just a great thing. Okay, so these tiny packages allow you to change modes of operations and consume tiny amounts of power and keep your battery running. Okay, so RF. What is it? Well, it's electromagnetic waves, and they range from 0 hertz to 300 gigahertz. That is what is called the radio frequency spectrum. Above that, we're getting into other things, close to light. Okay, but the powers that be one day said 300 gigahertz is the highest frequency that I'm going to call RF. Okay, so the wavelengths implied by the speed of light, which is 300 million meters a second. And the relationship between them is the wavelength is the speed of light divided by the frequency in hertz. So the wavelength in meters, speed of light divided by the frequency in hertz. Okay. So that's, and something else that's gone on, as I've told you about, and then there was DSP. When we wanted to get away from all those old analog circuits and we had A to Ds, we could turn signals into digital numbers, and we want to crank through these things digitally. I remember my first digital signal processing problem was in the early 1980s, and I went with digital signal processing. What is that? I got to work on TI TMS 320C10, which was the TI's first digital signal processing chip with the Harvard architecture, where it would do multiply, accumulate, bring in new data, and get ready for the next one in one tick. That was just a massive innovation back then. I think the clock was a megahertz or 2 megahertz. Wasn't that right, Joe? Well, what did you have in Speakeasy? What did you have in the early stuff in these systems? Was it TI parts? Yeah. Okay. This is Joe Mottola, by the way. So anyway. Okay. So what do we got now? Look at this. This is an older part. We thought this was great. My grad students thought the thing was just fantastic. You have these unbelievable GPUs, and the PS3 and an Xbox 360 got 100 watts of power and will not come close to it. The performance that you have in a Tegra K1 is sitting in many of your phones and burning 5 watts at most. That's when the thing is flaming. They moderate it by turning it off a lot when it's not needed. But that isn't the end. Kepler happened in late 2013 and near the beginning of 2014. And that thing is unbelievable. An 8800 GTX, many of you probably still have those NVIDIA GPU cards in your computer, and this thing burns under 2 watts when it's every functional unit in the thing is flaming, and outperforms an 8800 GTX, which many of you had in your gamer computers as little as 3 or 4 years ago. It's a revolution. Just utterly unbelievable what is happening. And we can do cognitive radio, real Bayesian network, deep learning, all this stuff, just completely tiny powers where it's going to utterly transform. Tim has done work. Tim, you know Tim O'Shea. He did a piece of work where the work said, I don't know what this signal is, but I'm going to do deep learning on it. And the deep learning is going to tell me what to do next. And are you talking about that this week? Thursday. I won't steal the thunder, except this completely unsupervised machine with deep learning did everything I'm telling you about here. It just figured it out on its own. It's amazing. And so it takes a long time on a general purpose processor, but with one of these GPUs, it's a lickety split. And this is going to go even faster. Just a revolution. You're here, you're doing it, you'll be doing it first while everybody else is going, what? Okay. Look, here's the problem we have facing us now. And I'm almost done. Good. Okay, so this is the RF allocations in the United States of America. It looks like it's full, doesn't it? Oh, it's just ugly. Where in the world? Look at this mess down here, the high frequencies. It's a mess. There's a problem with this chart. When you carve things up in pies and say, AT&T, here's your pie. And United States Government Air Force, AWACS plane, here's your pie. And, I gave it to the AWACS plane. Have any of you seen AWACS planes fly over lately? Nope. So that channel is utterly devoid of signals, but it's allocated to them. That is a waste of resources. So what you want to do is figure out a mechanism for sharing many of these frequencies. That has begun to happen in a big way, because we just do not have enough capacity to transmit all the data you want to transmit in these phones. You want to look at every YouTube video that's funny that comes along. And you got to be able to get the YouTube video from the Google servers to you. That requires capacity. Capacity is equal to efficiency of how I'm putting the data together, and then enough spectrum to transmit it wirelessly. Because the last time I looked, I don't see many of you plugged into an Ethernet jack. Yes, exactly. Okay. This was 3.55 gigahertz allocation about a year and a half ago. This is where it was going to be allowed to happen. Now you think the yellow is where it was? Oh no. That's where 3.55 was not going to be allowed to happen. How much of the United States population lives where those lines are yellow? More than 90%. So how much market was there? Zilch. There was going to be no market. But NTIA did not want you having 3.55 gigahertz in this area, because there's radars, there's from ships, airplanes, etc., that operate in these bands. So I said, we don't need to do that. So we can figure out how to do this. And it got delayed and delayed because, maybe I wasn't persuasive enough. But finally we were believed, and I talked him into helping me. And the two of us went out to near a Navy radar system. We were doing allowed border driving. And we could prove that we could hear these radars 100 kilometers away with zero trouble. And we wrote letters to the FCC when they did the notice of proposal rulemaking from 3.55 gigahertz. And this is gone. Totally gone. We took 90% excluded and turned it into 95% included. And when you have that kind of idea and you realize how much money that is worth, it's billions of dollars in that market, and you have the ideas, you've done a good thing for yourself and for others. So the thing on the left is the spin 43 radar, upper left, the spin 43 radar. Thing on the bottom right is the AWACS. They're in this frequency range, and everybody wants to protect them. Please don't do this. And of course they want, but I'll allow you to do it if you'll give me a few $1 trillion to build a new system that will not operate in these bands first. Well, I don't know whether we made them happy or unhappy that we proved that you can operate in these bands with them. And that's exactly what we did. So here is an announcement from the Wireless Innovation Forum that says a company was CEO'd by Ia Tarazi called Federated Wireless. And Google have been asked by the Wireless Innovation Forum to sit together and figure out these protocols for how to share this 3.55 gigahertz band after we proved that you could use it. And Joe and I and Jeff Reed and Charles Clancy are co-founders of Federated Wireless. This is truth in advertising here. I don't toot my own horn, but it's a big deal. Okay. All right. So here's the rules. Came out on April 21, 2015. And we had a lot to do with the rules, and it's a good thing. But GNU Radio is the thing that made this possible. Tim and I took a user B210 and some software and said, here's how it works. But we were standing back without a very sensitive receiver in the B210. We have no major LNA. crummy little antennas with crappy coax, and 50 kilometers away we were hearing this radar. So what happens is radar comes, ship comes near the shore. We hear the radar. We tell all the people using 3.55 gigahertz as a shared commodity, turn off. When the radar is gone, I'll tell you, you can turn back on. That's how the whole thing works. I mean, it seems really, really simple, but nobody believed it till we proved it. Okay. All right, look, here's what's up now. This is a big, huge deal. And everybody said this silly auctioning off the spectrum was just never going to work. Nobody was going to buy it because they couldn't figure out sharing and all this other stuff. And it only utterly overwhelmed the system with hundreds of millions of dollars just for research from the billions and billions and billions the auction gave us, including now the ability to do research in this band here. Okay, so guess what? They want to exclude all of California from 1700. And guess what Tim and I are going to do? Exactly what we did before, except we know the signals, and I'm not going to sit here and give away my intellectual property. I'm not that dumb. But we can easily protect this band even better than we did with the Navy. So it's just preposterous. These people are, I don't know what they're thinking. Anyway, okay. So this NTIA is freaked out about interference with airplanes and SATCOM. But we've showed them how to do, we're showing them how to do protect it. It's easy. And we're going to usurp B210s and a laptop computer and show them we can protect these bands. This is awesome. You've got these fantastic tools in your hands, and it will make you serious money if you use your brain and act on it. Or have a lot of fun. I mean, do whatever you want to with it. That's the reason the thing's been open source since the beginning. Okay, so 50% of the market will be cut out if you cut out all of the Southwest United States, because there's a lot of people living in California and Arizona and so forth. Okay, so we know how. All right. So we've come a long, long way since Spark Gap. And one of the things, the basic intent of this talk was to explain to you that you are in a privileged position. The privilege you have is you are aware of and know how important this GNU radio stuff is. It took us years to get approval for open source software to be done by all sorts of folks and used for their daily work. And we've done well. GNU radio's doing well. Matt's done well. With Edis Research, which is now a wholly owned subsidiary of National Instruments. We've left all sorts of people using GNU radio around the world, and you here are why everybody knows that GNU radio is important and why things are going well. Every time you pick up a new part and say, I could do this piece of software radio or cognitive radio or whatever, using this piece right here, it would reduce my size, weight, and power, or give me the ability to do something I never could do before. And you contribute it back to the ecosystem. We all benefit. Everyone benefits. As a taxpayer to the United States government, you are not paying $1 trillion for the development of the same modems over and over and over and over and over again. Because that's exactly what happened before open source software in the form of GNU radio and some other things took hold and began to take over. You have contributed it back to the good of humanity by doing this. I'm not exaggerating. It sounds like it's an exaggeration. I assure you, it is not an exaggeration. Open source software and software radio is going to be a huge deal in wireless communications, and I still notice that everybody here is wireless, for the next decade and beyond. It's important, and I thank you for being a contributor. Any questions? I was doing more preaching than, yeah.
You mentioned, working in amateur radio back in the 80s.
Yeah.
What about spectrum protection there? I mean, because that's always an issue. They're always trying to take the bands. We lost the 220 band and we're always under.
Yep, that's a very good question. My amateur radio call sign is November 4 Hotel Yankee. I've been in 4HY since 1976, but I was licensed in 1964 when I was 10 years old. Every single thing about my life, both my ex-wife and my wife, are hams. There's my wife standing back there laughing at me. She's an extra class ham. Just everything about my life is determined by being a ham radio operator. So naturally, I care a whole lot about protecting the amateur radio bands. The one thing you can say, I can say to you here now about amateur radio is, a lot of you are out there taking your U-Serves and you're plugging them into an antenna, and you're going, hey, this is fun. And you did not care a whit about checking to see whether or not what you were doing was legal. Almost 100% of you are violating the law of your country or the country you're visiting every time you turn one of these things on. But in the amateur radio bands, especially above a few hundred megahertz, almost every single thing you can do is blessed by the communications authority that have granted you an amateur radio license. You can do it for free. You are allowed to and encouraged to do experimentation and emergency communications if you're in the United States. It's the most fantastic place, and I suggest you go and check. Morse code is no longer required. You could pass enough to put that U-Serve on hundreds of megahertz of bandwidth above a gigahertz. In the United States and elsewhere in the world, you could just put hundreds and hundreds of signals on the air legally. Okay, all right. So 220, the loss of 220 was back when UPS was bribing its Congress critters, and they were beating up the FCC in order to take over and provide wireless communications, because another company had stolen AX25. The company this time that stole AX25, the guy that stole it came and said, I really thank you for doing that AX25, and now let me help you build a microsat spacecraft computer. I want to do that because you gave me the AX25. The company that did the wand, the first wand in the shipping company, Zebra Stripe wand AX25, what company was that? Federal Express. UPS wanted, and his name is Jim. Jim stole AX25 because we didn't patent, copyright, or anything else, and gave all the code away and put it in a wand and made the company Federal Express. Okay, so UPS was mad because Federal Express could have its fellow or gal with a package come out and swipe the package. It would go back to the truck, and they wanted a way to get the signal back home, just like Federal Express did, and they were determined to bribe. And they bribed their way into it. And then they didn't use it. They didn't use the band at all, and they were allowed to sell it off. Okay. So then we had another political thing happen. There was a Powell up here and a Powell down here. And the president up here who liked the Powell here, who liked the Powell down here. And this Powell was called chairman of the Federal Communications Commission. And these fellows sitting way up here, sitting down there on Pennsylvania Avenue, decided his buddies in the power industry needed to be a part of the IT revolution. And so they wanted to cash in on all this IT stuff, but they didn't want to do wireless. They wanted to do wired, because they had wired infrastructure into every house and building. And that was called broadband over power lines. They said, we will put signals from DC to daylight on these power lines, and they will never commit. They will never interfere with anyone. No signal can possibly leave our closed system power. And we had to prove with U-Serves and spectrum analyzers, etc., that they were putting more signal out into the air than they were putting into the houses and buildings, etc., because they did not understand that maximum power transfer happens when the impedances are equal. So they had reflections everywhere and the power was going everywhere. So a lot has been learned about this now. And the Spectrum Defense Fund at the American Radio Relay League is the most important advocacy fund in all of amateur radio. If you do not understand how important it is, you don't remember these stories I'm telling you, or you're not aware of the constant assault which we find our amateur radio bands. Now the one good thing we have, and then I'll quit, I promise. Amateur radio operators, where are they? Exactly. My point, thank you. Everywhere. They're in Congress. They're CEOs. They're bankers. They're everywhere. You take a really well-off guy's toy and try to take it away from them, and they fight back. And the Federal Communications Commission and the Congress critters and the White House, etc., have learned that amateur radio operators have zero intention of taking prisoners in the next war. Okay.